Welcome to ISSCC again. My name is Edith Beignet and I'm the Technical Program Chair of this year's conference. I'm really happy to introduce today the first plenary session. We're going to have two plenary sessions during the virtual conference, one happening today and the second one happening tomorrow, with a total of 4 plenary talks. Our first session today, we're going to have 2 talks. The first talk from Aart Geus from Synopsys and the second talk from Marco Cassis from ST Microelectronics. Let me first introduce Dr. Aart Geus. Dr. Aart Geus is the Chairman and Co-Chief Executive Officer of Synopsys. Since co-founding Synopsys in 1986, Aart has expanded the company from a startup synthesis enterprise to the world leader in electronic design, automation, silicon IP, and application security testing. Aart committed his unflagging energy to successfully leading Synopsys and the semiconductor industry through the technological and economic challenges inherent in advancing electronic design beyond the rate of Moore's law. Under his direction, Synopsys has consistently demonstrated innovation leadership across its portfolio, including emerging fields such as functional safety and autonomous design. Considered the world-leading expert in EDA, Dr. Aart Geus has been recognized not only for his technical achievements, but also for his contributions to both business and community, with multiple awards and honors, including the IEEE Robert Noyce Medal and IEEE Fellow, Global Semiconductor Association Maurice Cheng Exemplary Leadership Award, Electronic Business Magazine's CEO of the Year, Silicon Valley Leadership Group Lifetime Achievement Award, Phil Kaufman Award for Distinguished Contributions to EDA, Silicon Valley Engineering Council Hall of Fame Award, Joint Venture Silicon Valley David Packard Award for Civic and Community Services, member in the National Academy of Engineering. Aart is a pillar of the business community, serving on the boards of the Silicon Valley Leadership Group, Applied Materials, the Global Semiconductor Alliance, and the Electronic System Design Alliance. He is also a leader in advancing a variety of causes, including STEM education, having created the Synopsys Outreach Foundation in 1999, which promotes project-based science and math learning throughout Silicon Valley. Thank you so much, Aart, for being the first speaker of our plenary session, and thank you everyone for attending.
Catalysts of the impossible. That's who we are. That's what ISSCC has always stood for, making the impossible happen. We've now entered the SysMoore era, systemic complexity, but with a Moore's law ambition. With it, chips are poised to massively change our world again. They are surrounded by 2 forces, silicon and software. Chips are in the middle. And if you ask, what do we want? What we want is smart everything. What do we need is 1000x. That's us delivering that. It's in that context that our joint job is to be catalysts of the impossible. Now, impossible is a big word. It deserves a big equation, and the big equation, of course, is an exponential. Those suckers, they grow like crazy. Now, we have learned to live a lot with it in our field, but now the whole world is confronted by exponentials. You recognize the new COVID cases here, one long succession of up and down exponentials as the disease transmits or recedes. The curve that we know best, of course, is this one. On a log graph, it's a straight line. And while it's very exciting to see what we've done, and I know there's some fluctuations and some slowdown, what is really interesting here is more the future. And just last year, Cerebras introduced a chip of chips that was a chip at the same time, actually was a whole wafer with 2.6 trillion transistors. At the same time, Intel with Ponte Vecchio had a set of chiplets, 47 of them together, amounting to 100 billion transistors. Enormous capacities. And so this is where SysMoore is going. One more exponential. I wonder if you recognize this curve. And actually, if you look at the right side, it is actually a perfect exponential. Now, you may not recognize it because it started a little bit before your time. This is 1,000 years that we're looking at here. And you can see the beginning of the industrial age where energy really made all the difference. The conclusion is clear. All of these curves, two of them absolutely must be flattened. The third one, the middle one, the one that we are in the midst of, needs to be fostered so that we can deliver the capabilities that will actually help with smarts these other fields. So let's have a look at that. And in that context, the semiconductor industry happens to be especially well positioned. Because against the lens of techonomics, we can see there was a lot of attention last year, a lot of messaging about shortages, about supply chain issues, also about big valuations. Bottom line of all of that, the entire world recognizes chips are important. But to me, what's really important is the forward look. And the forward look is all about smart everything and what that takes. And clearly, we're seeing this all happen at the very moment where Moore's law continued to grow, but has flattened somewhat. At the very moment that big data, digital twinning, and machine learning all are coming about, demanding this massive push towards more capabilities, towards the SysMoore era. Now, in order to get there, it takes funding. And the good news is the semiconductor industry has done very, very well. As a matter of fact, past year, it went beyond 500 billion in revenue. Actually, I prefer to call it $500 billion. Because if we extrapolate on this, we can already see that by the end of the decade, semiconductors most likely will have passed 1 trillion quite well. So using trillions, there's a lot we have to do. And if we look at the demand, we can see it growing very rapidly. Here's the data, and you can see that by 2018, already the amount of data created by machines is massively bigger than created by humans. You can also see that in the last decade, the increase in computation that has gone in machine learning is moving at a very, very, very rapid clip. And so the result of all of this is that while for the last 50 years, Moore's law really has been a technology push that made new things possible, now we see an economic pull where every market is essentially looking at big data and smarts as a way to extend themselves, make themselves smarter. And with it comes the pressure, but also the opportunity of a major push in technology. Now notice how I split consumer here into health and into climate. Well, in health, I recently discovered Michael Snyder. He is a pioneer in medicine, actually a well-known person working at Stanford in charge of the genomics department. And what he has done is collected data for a cohort of one, meaning there's only one patient in it. He is the patient. And for the last 10 years, he has collected pretty much anything he could get his hands on his own body. He wears 4 Fitbit/smart watches, collecting continually. And what's of interest, of course, to us is he has 2 petabytes of information about himself. Just imagine a group of only 500 patients, and we would have an exabyte. Exabyte is big. And so all of this drives one thing, which is this need for massive calculation, because, of course, this data can be super helpful. He himself diagnosed that he had Lyme disease. Amazing. But assume that you can do research on one person or on many people. We will find correlations that are extremely valuable going forward. So all of this needs a technology system that has different levels of abstraction. Starting with the silicon level, we then move up in our field in logic and physical design, of course, microarchitecture and RTL. Then we have the watershed between hardware and software. And the software is grossly simplified, but essentially you have the drivers, the operating system, the machine learning, the big data, and ultimately the applications. And if you look at each one of those, they're essentially high abstraction at top level, more and more detail as you go down. Now, in all of these triangles and this level of abstraction, there are metrics of success. And this is a very powerful system. Quality of results, time to results, cost of results. It's powerful because they always compete with each other. Now, if you're more marketing oriented, you call this better, sooner, cheaper. And this way of thinking applies to so many different problems in life, maybe with the exception of your spouse. Do never use cost of results on your spouse. All kidding aside, there's another lens. It is a behavioral lens. At the top level, it is opportunity. And opportunity is really understanding what technology could offer in terms of new value. And of course, is the domain of entrepreneurial thinking. At the bottom, you have optimality. How well do we implement the intent? And there, that is the realm of the engineer. In the midst sits optionality, choices, the need for decisions in terms of directions. It is how do you impedance match to opportunity and down to optimality. And that, of course, is the job of architecting. And so with those two models, there's a lot of things we can do as we think at the problems going forward. For starters, let's look at this triangle in the middle that really sits at the key intersection between hardware and software. This has become especially important in the last few years. I took the liberty to illustrate on the side emulation machines, because it's now possible to run software on a model of the hardware that doesn't exist yet to optimize it. But if you look at this intersection, and we want to really squeeze 1,000 or more X out of this entire stack, it starts by focusing the architectures, essentially reining in what they can do. What better example than a GPU that has really focused on one thing, managing pixels? And here, of course, there's a lot of effort that's going into that. At the same time, at the bottom of the triangle, we still want to broaden it and have way more capabilities, capacity, and speed. And in that realm, we now see the coming about of 3D IC, abutting chips very closely and stacking them on top of each other. Let's have a look at 3D IC. And whenever we talk to people about this, what immediately comes up are three questions. The first one is, how do we deal with the systemic complexity of this? That's a lot of chiplets. Secondly, how do we actually find optimal solutions among multiple chips in terms of PPA? And lastly, how do we verify with the tools that exist that this will actually work? So let's zoom in briefly into each one of those, starting with scale. And really, from my perspective, scale is fundamentally connectivity and connectors more than anything else. And if you look at the bottom right, the notion of creating the new bumps, I was quite surprised, actually, seeing the following timeline. And what you see here is essentially how connectors have become way, way, way smaller. And the density, which is the first number under these pictures, has gone from 10 to 10,000 or more bumps per square millimeter. That's enormous. While meanwhile, the power to actually transmit a signal has gone steadily down. So excellent, excellent progress in that. Now, to design with all of this takes a lot of effort. And optimality starts by understanding the top-down picture, how the different multiple chips fit together, how they are connected. And then there's a whole set of mechanisms that are specialized to optimize different aspects of the chip. Now, there are many here. I won't go into detail. Let me just highlight the middle one at the bottom. The necessity to also revisit testing. How do you test a multiplicity of chips, where each one in isolation may be considered as being functional, but together it still has to be proven. And then, of course, there's a lot of verification and optimization that goes into this. And notice that in the pictures that I have here, there's quite a bit of colored surfaces. And this, of course, has to do with the fact that thermal effects are absolutely essential. We know and we use inside of transistors stress for speed, but we don't like stress on chips as they tend to warp, and that causes all kinds of issues. Be it as it may, there's a lot of EDA that is now going into this, and actually 3D IC is alive and growing very rapidly. Let me give you a 20-second sort of EDA primer. And EDA is relatively simple conceptually, which is that if you can capture data, you may be able to model it. If you can model it, maybe you can simulate. If you can simulate, maybe you can analyze. If you can analyze, maybe you can optimize. And if you can optimize, maybe you can automate. Actually, let's not forget, the best automation is IP reuse. It's the fastest, most efficient. Now, it's interesting to observe this because if you look at the bottom layers, what we have been doing in our field really for 50 years is we have built digital twins of the thing that we're still building. And if we now say we're going to deliver to our customers and the world 1,000x more capability in chips, the notion of metaverse, some call it omniverse, neoverse, whatever you want to call it, is becoming extremely powerful because it's a digital view of the world as simulation of it. We already briefly talked about it, looking inside of the human and simulating how it functions. Let's look outside at climate. And when you talk about climate, we all know that is a high degree of urgency there. But what is so interesting about climate, it is a great representation of scale complexity in so many different dimensions. And meanwhile, there are many, many more. That's what's illustrated here. And all of these come together and multiply with systemic complexity. And by the way, on top of that, we increasingly have more historical data that we can all model together to attempt to predict the future and specifically the temperature of Earth. Now, I've been interested in this for many years because I consider this the single biggest danger to humankind. And for many years, I've been looking at the predictions all the way back to 75. And if you look at these predictions over time, they all end up roughly at the same place. And they all become more and more accurate, especially as past data can be used to critique and refine the model going forward. All the way to the predictions that by 2020, we would be about 1 degree above industrial time, pre-industrial temperature. And this is happening. I don't have to tell you how big an issue this is, but it is useful here too to look through the 3OP lens here. Starting with opportunity. And our opportunity, of course, is to keep growing the standard of living while at the same time submitting to the necessity of sustainable environments. Well, we've done pretty well. The standard of living actually has grown enormously well, especially in the last 50, 60 years. And yeah, there have been a number of catastrophes that have been growing, but how bad can this be? This almost be part of cost of results. Meanwhile, we're doing fine, right? But when you look a little bit deeper into that, it doesn't actually take much more than manual intelligence to figure out that the CO2 has been increasing like crazy. And then from there, gradually build the models that show how that impacts temperature. And then, of course, you can close the loop, because from temperature, you can figure out that that is what causes all these weather disasters, fires, and so on. And we can also close the loop the other way, which is that it is our drive for higher standard of living that makes us use way more energy that causes the CO2. You notice all of this crisscrosses the word optionality. And optionality is decision-making. It is also the moment of responsibility. And if I have one fear that's bigger than anything else here, is that the issue we're facing is actually time to results. We actually know mostly what is to be done, partially how to do it, and we have the instruments to go much faster. We need to take action. So part of it is for us to deliver the smarts that can look at all these problems and advance the state of the art. And so let me go back to EDA and now add machine learning. And it's sort of uncanny how similar these levels of abstractions here are too, because one collects a lot of data here too, one creates models, one learns from them, one infers from them, and then gradually some actions, optimization are possible, with the hope to ultimately have all kinds of autonomous behaviors. Well, it's a little bit like eat in your own restaurant, and we are doing that because we're now applying AI in EDA. Here's a sort of a brief history of EDA. It starts with really simulation in the early days, then putting it on the computer, the layout, and a number of other actions. And then there's sort of a watershed moment. And the watershed moment is synthesis and automatic place and route. It happens to be when Synopsys started. We're not the watershed, but we were living on this intersection between computer-aided design morphing into EDA, electronic design automation. And I said, these are great automation steps, and immediately they got amended by the notion of IP reuse, which is a fabulous step. Things got more and more complicated, more and more powerful, and then we arrived at this notion of fusion. And this is a very important one that I'd like to briefly explain. And fusion essentially takes into account that different programs that we use in designing chips, such as synthesis and place and route, have many algorithms, as illustrated here in these hexagons. Sometimes they go in the same direction, sometimes they fight each other a little bit. And the idea of fusion is to recognize which things can be shared, then complement them with the other activities of each one of those tools, and amend them substantially by a whole set of diagnostic capabilities and other things that have to work together. And what you see here is really the notion of many technologies all working together as a team. And we have done this in our company. And you can see here that the results over a large number of real designs have really been remarkably good. That's not the reason I'm showing you this. The reason I'm showing you this is because this is the foundation that is necessary for the next step. And the next step starts with small steps, which is machine learning is literally in every tool optimizing algorithms, understanding design better, etc. But the next big step is really applying AI to a whole phase of the design flow. And so let's briefly look at how we did that. Starting with Fusion today. So you're essentially trying to optimize the space, and PPA are, of course, the three aspects. And this is a simplified version, of course, of it. And you explore this space by essentially trying out different things. And because Fusion compiler is pretty fast, you can actually look at a lot of different areas of the design and gradually find more and more results. And maybe you find some groupings that are of particularly high interest that you can tune more towards your final design. Now, the question is, what if we could use AI around this? And so it starts by wrapping some compute and then a capability that we refer to as DSO, not design space exploration, but design space optimization. And then we let essentially the system learn from what it's found, use the existing data, and do many, many more experiments until it can find some regions that are particularly promising. They may be the same as the human, they may be different. Now, what I've just shown you is the PowerPoint version of this, of course. And in full disclosure, in August, I shared the first real examples at a conference called Hot Chips that you may want to look at the proceedings because there are many, many interesting examples. So I'll share two of those just to set the principles of how we made this work. Here's an example where we had a starting point. We had an objective set that the design team wanted and the best results that the human team could achieve. And then we let DSO.ai loose on this example. There, you can see it now computing the different points. And I've seen this thing 1,000 times by now, and I'm still rooting for the algorithm to see if it can go further down to the lower left. And indeed, there's still some more points that it can find. And then suddenly it arrives at sort of this point of, wow, still some more. There we go. Substantially better than before. But you know what blew me away when I saw the result? What I saw was this. And I had seen this before. 35 years earlier, introducing synthesis, we had only two variables, speed and area, and they traded off. And we had exactly this. We called it the banana curve, the trade-off curve. Well, we found it again here, except in this case it's automatic, and now, this was the untrained version. Let me now run the trained version where it has learned from the past. And what you will see is that in almost no time, with very few attempts, it gets still better results. So this was the first example, and it goes back all the way to March 2020, so not that long. Since then, we have many more examples. There's one more I want to show, and there's a reason I want to show it, because this happens to be a CPU core that a company did with us, and actually they run all of this themselves. And you can see many, many attempts and steady state working to the lower left there until it finds the best possible solution. And then here is the trained version that can find this in a very short amount of time. Now, why did I show you this example? Because we got feedback through the QR, TTR, COR lens directly from our customer partner. And they signified three things. First, the quality of results was substantially superior to what the manual work had been able to achieve. Secondly, it was in a fraction of the time. Literally, the time had gone down from months to weeks. And third, these examples were done by one person instead of the manual one, which was a real team of experts. And so this is where we were literally in 2020. And I have many more examples I'll show you just in a minute. But I want to take a little sidetrack now, because many people say, yeah, but what about verification? Well, verification is interesting because remember, the stack here, intent to implementation. Well, design looks downward, ultimately ending in physics. Verification actually looks upward to function. And it continually verifies that what you have implemented still represent what you intended to implement. And of course, in both of those cases, one can go a little deeper into it. They apply to each triangle, they apply to the whole flow, which is essentially specification to specifics. And the going down is intended to be correct by construction. And actually, a lot of it is correct by construction. The pathway down means extracting a new model and then comparing that to the original specification. And to be honest, I'm not sure if in the case of issues, the spec is not good enough or the correct by construction. But the reality, of course, it's a combination of the two. Now, in both situations, you have different forms of QR. For verification, it means more the quality of the coverage and the time to get there. So let's have a look at verification a little deeper. And here, of course, there are many, many tools and techniques illustrated here, left to right over the design flow, including the post tape out, and then including the life cycle, where for many chips, we now need to be able to diagnose if the chip is still functional while it's been in the car for 5 years. I also know well that the cost of fixing a bug, of course, goes way up the later it is found, which has brought about the mantra of shift left in the industry of verification. Now, it begs the question, so where are the bugs found? And fortunately, we have about 30 customer partners that share data with us. And using sort of the Grace Hopper representation of bugs here, you can see that in simulation is far and away where most of the bugs are being discovered. And so that begs the question, well, is there an opportunity to do better on this? Because the way it's typically done now is the verification engineer sets a target for coverage, and then one starts working with a variety of vectors manually and sometimes random vectors to see how well the coverage is. It quickly runs out of steam. So this is really, really old way. And so constrained random has actually had quite radically good progress in getting to much higher level of coverage. And now the question is, can we amend this using AI to get close? And if you can, improve both the TTR and the QOR, if you can get higher at the same time frame, or even better, get to the actual 100% coverage. And so in order to do that, it takes a lot of effort. And let me give you sort of a similar view of DSO, but now for VSO, starting with a simulator. And the simulator looks at, of course, a state space that is enormous. And the transitions in the state space are even more enormous. And by the way, there are a number of those that can be flagged as being illegal. So the engineer sets a set of targets, states that he or she thinks will be good at covering a lot of the functionality. And then one starts actually running this and proceed on finding a lot of, or arriving, I should say, at a number of these nodes and covering them. And if one is lucky, one can maybe find a place where a legit transition occurred, and that is the beginning of finding what the real bug is. Now, if you look at this, you can also see that there's sort of a dark space there, and that feels like a coverage hole. And of course, this thing is so big, there are a lot of black holes in this. And the question is, can we now use compute and a VSO capability, so verification space optimization, to arrive at these black holes, focus the search, or have the VSO actually find itself where these black holes sit? And so you do this by, of course, taking information from what we've learned before and driving the selection of the seeds and the vectors that will be used. And so let's this thing loose on it, and it has to work pretty hard because it's very deep to arrive at certain places. But if one does this well and run it long enough, indeed, we will be able to find some additional bugs. So again, here, what you just saw was the PowerPoint version of the algorithm. I have three real cases that I'd like to share with you. The first one is a mobile apps processor. And targets is set here, and here is the constraint random, the traditional way of doing it, and it's making excellent progress. What's not visible on this graph is that you need to go another 1000x this, and then you will actually arrive at the target. Now, we let VSO loose on this, and it was quite remarkable how quickly it could find a very good solution, and of course, in a fraction of the time of what we had before. So much so that the engineer decided, hey, I'm going to raise the target and improve the quality of results of the coverage out of this. Here's the second example. A GPU. And GPUs are interesting because they are very well optimized, understood regular structures where for years the testing has been improved and optimized itself. And here too, actually the real runtime to get there is about 1,000 times longer than what I show. But there is definitely very, very concerted progress in what they do. Here's what the VSO capability was able to achieve. It arrived at the target dramatically faster than what the other algorithm was able to do. My third example is very different again. And in this case, we're looking at an accelerator in a data center. And data centers, for good reasons, are very picky about quality, because if any one of their machines goes down even for a fraction of the time, that is major economic value. And so they do an enormous amount of testing, not 1,000 times more, but 10,000 times more than what I show you here. And so they're very interested in how to accelerate this. And here too, the results were just truly extraordinary, because in a very short amount of time, one was able to meet the target. And then, of course, the engineers have to decide, do they want to raise the target further, let it run more? And invariably, they always decide, let it run more. So now let me come back to DSO and show you some of the tremendous advances that we've had recently. Now, to do that, let's revisit levels of abstraction. You recognize it here, but there's a better representation from Dan Gaschke and his student Kuhn that I've always admired, where you have behavior, structure, and layout all in the same graph. And think of it as a funnel that goes to the inside, and in the middle of it is the tape out. And so the idea is to refine the design by essentially spiraling down that funnel. And you would start, of course, with software at the top, then the architecture, the design, and you keep closing the loop with verification. Now, if you do that, there's one more step to take, which is once you're taped out, you go to manufacturing, and there's a variety of steps in that. And then you close the loop by bringing up the circuit with the software, and hopefully not too much debugging to be done. And so what I've shown you so far on this is that we were working very much with DSO.ai in this ring of doing big blocks, chips, and so on. The next experiment we've done recently is actually to go way to the center, close to the physics, in something called DTCO, Design Technology Co-Optimization. And a number of years ago, we illustrated this as multiple steps, but viewed through the end result in mind. So we start, for example, with ab initio, literally atomic level simulation, TCAD, layout, and then the basic devices and the interconnect. And you extract the information for that to get a SPICE deck and the layout verification rules all packaged together called a PDK, a process description kit, which is where most people start. And if you have that, you can then develop a cell library and the interconnect to go with it, synthesize and place an route from it, and go all the way to a final block. So here's what ideally we like to do. Be able to make a change in, let's say, the manufacturing recipe and see what the impact on that is on a specific block of value. Now, how do you do that? Well, you actually fabricate it. Two problems. Very expensive, and it takes a long time, many months in most cases. So instead, what if we could simulate, and actually if you can simulate a little bit, why not simulate again and again and again, so that you get data and can apply machine learning to the improvements. Well, this is exactly the direction that we've taken. And we've done it for two things. One, the power network, and two, for the interconnect layers. Let's start with the power network. And so here, the objective is to optimize the power network, and there are many different variables on it. You see them marked in green, and improve specifically IR drop and the electromigration that goes with that. And we have, in this case, a best solution. We start the optimization, and it explores a lot of the space while gradually moving itself up to the upper left, which is where the best results actually are supposed to be. And so here's the best solution, and you can see a quite fabulous lower IR drop than before. So that's absolutely going in the right direction. Now let's go to the metal layers. And for starters, we'll optimize the pitch between the different connectors. And here, again, we start off the optimization. And as you can imagine, there are many layers, so there's a lot of opportunity to tune this. And if we look at the best results, 25% better timing. Now, I don't want to give you at all the impression that everything will meet that, because that is so high a number, but it does show that there's a lot of room in these optimizations. One more time, the metal stack, but this time we'll look at the thickness of the layers. And of course, that implies touching resistance and capacitance. And here too, the optimization actually quite rapidly moves the solution substantially up to the left. And you can see, again, cumulative value improvements that are significant. And so, to me, what all of this says is there's a lot of margin hidden in systemic complexity. Now, if we are able to do this outer ring and the DTCO ring at the middle, the one that I've always wanted to have done, all the way back to the 90s, is cell library optimization. In the 90s, there was a lot of discussion on how many cells should one have, because there's so many potential permutations and so many options from a physical perspective, electrophysical perspective, to design it. And so in this experiment set, what we're going to do is select the best subset of cells from a library, again, against a microprocessor core. So these are all designs for against real cores. And you can see the starting point and the gradual improvement in the right direction. And I would venture to say that cell selection has a pretty substantial impact on the outcome. And here you see it, timing 35%, power 10%. That is enormous. Of course, mileage will vary depending on the core, but this is a great experiment that will undoubtedly bring more opportunities. Now, there's another variation on libraries that is actually quite tricky and recent. And that is that we're now looking at cell rows of different heights. And so there's a short and a tall. And just to make it more challenging, there's also two types of cells, the ones that are double heights or single heights. And so here the challenge is, can we optimize the ratio of the short versus the tall rows? And you can see the optimization in the works. And again, quite substantial benefits on a problem that, in my mind, no doubt, this would be very, very challenging for a human to actually select the right answer. So one more situation that is very important, the remastering of a design from, and then we're talking about this big ring again, major design blocks, and you can remaster really in 2 dimensions. One dimension is to take the design and actually move it from one node to the other. The other dimension is to say, oh, you know, there's an onomic opportunity in my design. The chip is selling well, but another customer would like a variation with something changed. So you move from design A to A prime. We have done both with exciting results. Let me show you the bottom one, because nodal transitions or remastering are really important going forward. And so we have an experiment here that starts as follows. You start in technology 1 with an original design, and you do 2 things. You implement it the regular way, and then you use DSO to see if you can do better. So let's quickly run this experiment to sort of set the ground results. Here is the best regular manual design, and then you can see that it's already working well towards improving on that. And so here is the new result. Now, I'm not really after this result. I just wanted to make sure that you see the whole experiment. Now we do the second part of the experiment, which is the same design, but a different technology node. Still similar, not too far away, maybe from a different foundry, but similar. And we do a repeat of the first part of the previous experiment, the manual design, the DSO-driven design, and then we do something different, which is we do a DSO-driven design, but with the learnings of the first node. So let's see how that comes out. And so we are now in the second technology, right? And you can see, I didn't do all the dots. You can see the original and you see the results clearly better than the original, but as expected. Now comes the question, what happens when you run with the learnings from the previous node? 2 observations. 1, it's as good, or in this case, even a little better than before. 2, in very few attempts, it got there. With other words, the learning was quite effective at getting at good results in a short amount of time. Now I have one more, and it's so recent, literally just a couple of days ago that I got the results. And I don't have the dots, but I'll give you the summary of it. So, just in. This is a 3-node tech jump. So now there's a big difference between an N40 node, here's the original design, 1 gigahertz roughly, and an N10. Now you say, well, yeah, it's a lot faster. Of course it's a lot faster. It's a technology that's much faster. Nothing novel in that. And now let's apply DSO with the learning of N40 on N10. And what is great is not only did it do just as well, even better on the speed, but it was able to reduce the power by another 10%, and of course do this automatically. Therein lies the power, because there's going to be a lot of interest going forward in designing chips so that they can be remastered in the next technology, because the life cycle of some chips is much longer than the degree of change of the technology or the availability of parts. So, one more last topic, and this is an exciting one because it's not only an advance in DSO, but also in silicon technology. And the idea here is being pioneered by one of our partners, which is to move the power network, which typically sits under the connectivity layers, to the back of the chip, and then make power available via through-chip power vias. That's the plan. Now the question is, how do you optimize this? And this is, of course, cool optimization, because we start from scratch with the hope that this will really help routability. And so there are a lot of variables in this effort, and including the fact that you can have certain leads that are always on, or some that are on and off, in order to save power. Now, just to understand, these colors are not different runs. These colors are rating the results on a 3rd dimension, which is IR drop, which is very important for a power network. And so you can see the red is obviously bad, green is great. And frankly, I don't like this representation that much because I can't quite see it so well. Whereas if we sort of 3-dimensionalize it, then it's pretty simple to find in the top left, the banana curve, except it's no longer a banana, it's a hyper banana. And the way you should think about DSO and the way you should think about AI in general, its power lies in the word of hyperdimensionality. you can bring many functions together and get better results, which exceeds what humans can do easily. Here you see the actual results of this, and so this is extremely promising going forward. You know, I've touched on a huge number of topics, yet just scratched the surface. Silicon to software, techonomics, EDA and AI, digital twinning inside of our body and around in climate change. We're now in the SysMoore era, where scale complexity and systemic complexity multiply. They don't add, they multiply. Because interdependency and complexity are great for AI. It can find those hidden spots that are so difficult for us to find. We now ourselves are using AI to design chips. DSO is a brain that sits on a large number of super sophisticated tools that all work really, really well together. And therein lies the essence. 7 years ago, I tried to paint a vision of interdependency on my favorite swooshes of silicon and software. And already then it was very, very clear. Technology and design, they need to be linked really, really well. Actually, design and IP also. IP and verification. Verification and the embedded driver and operating software. And of course, let's not forget security, safety, all towards building applications that change the world. And those in turn are surrounded by zillions of IoTs cranking out data. That is the picture to optimize. And now we're adding AI to make it happen. That optimization is sort of the equivalent of saying, hey, this is teamwork between technologies, teamwork between tools. Absolutely essential. But you know, from my perspective, what's even more essential is represented here. The version where it's about the teamwork between us people. You know, the hand that develops the computer on which the EDA is written that can help develop the next computer to write better EDA and so on. That circle is the circle that has brought about exponential achievements. You know, so often we say, you know, success, it's the sum of our efforts. No, it's not. It's the product of our efforts. A single zero and we all sink. Great collaboration and we all soar. We make a change. We, together, catalyze the impossible. Thank you and be well.